Hi everyone, this is Mr. Zarzak, and in this screencast, I'll be discussing the physics of how rainbows form and how they depend upon the phenomena of refraction. Refraction, if you remember, is when a light wave changes medium and as a result changes speed. If that light wave is incident to the boundary between two different mediums at some non-zero angle, that refraction will be seen by the bending of light. Before we can discuss rainbows, we really need a little background information on how we perceive color. What you see here is what we call the visible region of the electromagnetic spectrum. What we perceive as visible light is actually electromagnetic radiation. The electromagnetic spectrum extends in both directions and encompasses all kinds of waves. You may have heard of some of these. They include things like radio waves, microwaves, X-rays, gamma rays, and the more familiar infrared and ultraviolet. As we move from left to right along the visible region of the electromagnetic spectrum, we go up in frequency, and as a result, the waves also get smaller or decrease in wavelength. The constant here is the speed. Light waves all travel at the speed of light, and so increasing the frequency has this effect of decreasing the wavelength. If we think back to our unit on sound waves, we interpret different frequencies as different pitches. Low frequency, low pitch, high frequency, high pitch. Well, with light waves, we interpret different frequencies of electromagnetic waves as colors. Just like we have a frequency range for our hearing, we also have a frequency range for what we can see. Just like there exists ultrasonic waves that are too high frequency for us to hear, we can think of ultraviolet as the colors of light that are too high frequency for us to see. We have infrasound, which is sound waves that are too low frequency for us to perceive. We can think of infrared as the colors of light that are too low frequency for us to see. Whenever light passes from one transparent material to another, it changes speeds or refracts. What's interesting is as you move along the electromagnetic spectrum, if you go up in frequency towards the blue end of the spectrum, the amount of refraction actually increases, or the light gets slowed down more on this end of the color spectrum than on this end of the color spectrum. And this trend of the higher in frequency you get, the slower the light travels when it moves into a transparent material continues. So much so that high-frequency light, like ultraviolet light, is actually absorbed out altogether. That light is completely stopped, and that light energy is converted into heat. This is the reason that on a hot summer day, a pane of glass will get really, really warm. It's because the glass is absorbing out the ultraviolet radiation and transforming that energy into heat. This also means that things like water and glass can protect you from ultraviolet radiation. Too much exposure to ultraviolet radiation can trigger cellular mutation, commonly known as cancer. And so the takeaway here is that if as long as you stay covered by glass, you can prevent yourself from getting sunburned. Think like you could work for an entire summer in a greenhouse without ever having to put on sunscreen. Back in the 1600s, Isaac Newton passed sunlight through a triangular piece of glass called a prism, and when he did, he observed that the sunlight seemed to separate out into these colors that we now call the color spectrum. He was then able to take these separated colors and then pass them through a second prism, and when they emerged from the second prism, the light was again white. This led Newton to conclude that white light was not a color in its own, but a combination of all the colors of visible light. This process of separating white light into the colors of the visible spectrum is known as dispersion, and it results from the fact that different frequencies of light are refracted by different amounts. Higher frequency light will be slowed down more than lower frequency light, which for us means that blue light is refracted more than red light and is seen to bend more when passing through a prism. Now, of course, when we pass white light through a prism, we don't see individual light waves. What we get instead is a continuous spectrum of color that results from this process of dispersion. And so again, white in itself is not a single color, but a combination of all the colors of the spectrum. Thinking along those same lines, black is not a color either, but merely the absence of visible light. A good way to think about this is if I was in a room and I wanted that room to be pitch black, I would need to close all the doors, shut up all the windows, and turn off all the lights so that no light was present, and I would interpret that as black, which is just the absence of visible light. Now, a prism will disperse light via refraction into the bands of color that we call the visible spectrum, but a glass prism or a plastic prism is not a rainbow. So now let's talk a little bit about rainbows and how they're formed. So here we have a picture of a double rainbow. Before we talk about the difference between what's called the primary and the secondary bow, let's just talk about the bow part. This arc here, this is the bow. And we can have secondary bows, we can have tertiary bows, we can have quaternary bows. Okay, the process continues, but every time we get another bow, all right, there's two things that happen. Okay, one, the colors are reversed, all right, and two, the bow gets dimmer and dimmer and dimmer the farther we get from the ground. So seeing the primary bow is far more common than seeing the secondary bow, not because it's not there, but because often it's just not bright enough for us to see. So that's the bow part of the rainbow. The other thing that we need to have a rainbow is rain. Now, not just any kind of rain is going to result in a rainbow. Okay, what we really need is more like a mist kind of a rain, so that our droplets are really small. And if the droplets are small, under about 2 millimeters, the cohesive forces of water molecules will pull the falling water together, and the water will form almost a perfect sphere in the atmosphere. The other ingredient we need to form a rainbow is we need a lot of light. And so typically, if you're going to see a rainbow, it's going to occur when you're near an area that one part of the sky it's raining, and then the other part of the sky it's sunny. So now let's focus on the processes that happen that result in the formation of the primary bow. I've included a picture of the sun here in our diagram to go along with our raindrop. And of course, notice that neither the raindrop or the sun are drawn to scale. Okay, I've made the size of the raindrop really, really big so that we can focus on what happens inside the raindrop when it's illuminated by sunlight. The primary bow we see results when sunlight is incident to the water droplet up here near its upper half. Now, I'm not saying that there's not sunlight that strikes all different parts of the raindrop. It's just this sunlight that is incident up here near the top, okay, that winds up creating the effect of this primary bow. When the sunlight enters the raindrop acts like a tiny little spherical prism in that the sunlight is refracted, or it changes speed inside the rain, and the different colors of the visible spectrum change speeds at different rates. Think the blue end of the color spectrum is refracted more than the red end. Now, there's other colors involved here, but I'm just showing a blue light ray and a red light ray to make the diagram easier to interpret. Okay, and you'll see what I mean here in just a second. Along this edge here, where the light is incident, we get refraction. The light travels through the raindrop to this end of the raindrop, and then a portion of that light will reflect internally. Now, some of the light will refract out, okay, and that light travels in a direction that never winds up reaching our eye, so that's kind of lost to us. We don't see it. It's the portion of the light that internally reflects here that we need to focus on. Because it's that light that when it hits the boundary here between the edge of the raindrop and the air below, all right, that the light refracts out again. And when this occurs, okay, we get another change in speed. And just like when we entered the raindrop up here, when the light exits the raindrop down here, you get a second case of dispersion, or in other words, the blue end and the red end of the spectrum are separated even more. Now, the change in speed for red light versus the change in speed for blue light is very subtle. There's not a huge difference there. And so even after 2 instances of refraction in the raindrop, okay, the 2 ends of the color spectrum are only separated by about 2 degrees. And they exit the light at this 40-degree and 42-degree angle, respectively. Now, what I'd like you to focus on here is not so much the geometry, which is already starting to look pretty darn complicated, okay, but instead the boundary behavior of the light. In other words, we can identify here that when the light goes from air into water, refraction occurs. And here we see the light hitting the boundary between the water and the air, and instead of coming out, it's internally reflected. And then again, here, this boundary behavior is the light exiting the raindrop, going from water back out into the air, and so that's the case of refraction. We need this refraction here in order to separate out the colors of sunlight into the colors of the visible spectrum. The internal reflection here just redirects the sunlight down towards our eye. We're going to be down here somewhere looking up towards the sky, and it's during this reflection here that the colors wind up flipping. This picture here is a little bit more accurate than the previous slide in that more of the colors of the spectrum are shown, okay, but it also makes the diagram a little bit more difficult to interpret. The important part here is that this process of refraction leads to dispersion, which is the color separation, and we get two instances of these, one at this boundary here and one at this boundary here, and the result is that we separate out sunlight, which contains all the colors of the visible spectrum, into those individual colors that exist in this narrow band between 40 and 42 degrees. If we look back at our picture of the double rainbow, focusing on the primary bow, look at what we have here. A narrow band where we see the colors of the visible spectrum separated out. Now, you might have picked up on this, all right, but on the previous slide, the red light was on the bottom and the blue light was on the top. So now why is it that we see it the other way when we look at the primary bow? What you need to understand here is that when we see a rainbow, we're not just looking at one or two raindrops, but we're looking at a whole bunch of mist in the atmosphere. Each of these little raindrops is acting like a little tiny little prism, separating out light or white light into the colors of the visible spectrum. If we peek up here at this raindrop, this is where we're going to see red, not because blue light and the other colors aren't being separated out, but because they travel along a path of light that misses our eye. It's at this angle of 42 degrees that we would perceive these clear drops of water actually as red drops of water. And a little lower in the sky along this 40-degree line, okay, these water droplets are also acting like little prisms. All right, the red light's coming out and all the other colors are too, but they're traveling down towards the ground at an angle that misses our eye. And so if we look here into the sky at this 40 degrees, the clear water droplets from our perspective appear blue. And so what we're seeing when we look at this primary bow is just a region of the sky that varies between this 40 and 42 degrees where little bands of water appear to be different colors, the colors of the visible spectrum. Now, what about the secondary bow? We can use the fact that the colors are reversed, so in other words, the red band is closer to the ground than the blue band, as a hint to help us figure out what's going on, and we can also use the fact that the light is dimmer as a clue to help us figure out what's going on. The secondary bow is going to occur about 10 degrees higher in the sky, so the primary bow is between about 40 and 42, and the secondary bow is between about 52 and 54.5 degrees. The process that results into the formation of this thing that we call the secondary bow is actually very similar to what we get with the primary bow, all right? But with the secondary bow, what we're interested in is the light that travels from the sun to raindrops that are higher in the sky but actually strike the boundary between air and water at a little bit lower angle along the raindrop. Again, when this sunlight, which contains all the visible colors of the color spectrum, enters the raindrop, it undergoes refraction, and as a result, the colors get dispersed or separated out just a little bit as light goes from air into water. Just like with the primary bow, when the light waves that are now traveling in the water strike the boundary between the water and the air, some of the light actually refracts out and goes off in this general direction, but that light never reaches our eye, so we don't see that. Some of the light is now reflected up towards this part of the raindrop. When the light reaches this boundary here, again, some of the light actually comes out of the rain droplet and goes off like this, all right, but some of the light also internally reflects down here. It's the light that's made it through this internal reflection, and then now one last time refraction, okay, that's bent down towards our eye at this bigger angle of between 52 and 54.5 degrees. The secondary bow is a little bit wider than the primary bow because we've got this extra case of internal reflection up here that causes the light to separate out a little bit farther. The light is also a little bit dimmer because, well, every time we hit the boundary, some of the original sunlight is refracted out, so we lose that light. And so the light that goes through here is a little bit dimmer than the light that went through here, and the light that passes through the rain droplet here is a little bit dimmer than the light that passed through the droplet here because some of that light comes out near the top. It's also because of this instance of two internal reflections, so one right here and one right here, that the colors are reversed. If we track the path of the light, we see that right at this point right here, all right, the red side and the blue side switch places. They switch places again here, and then they switch places one more time here, all right, which is one more time than we got with the primary bow. Hence, blue and red are now reversed. Now, if you're feeling a little confused or overwhelmed by all this flipping and bouncing, okay, well, don't, all right? The real big takeaway here is not about 52 degrees or 54.5 degrees or 40 or 42 degrees, but instead it's what's happening when waves strike the boundary between one medium and another. Here, the light passes from air into the raindrop. That's refraction. We're going to get a change in speed when the light changes medium. Over here, we can see the light hitting the boundary and not exiting, and so it's what we call internally reflected. That also occurs right here. And then over here at this boundary, the light exits the raindrop, so here we have the case of refraction. Much like with the primary bow, both internal reflection and refraction are involved, all right, but whereas the reflection really just takes care of redirecting the light down towards our eye, it's this process of refraction that gets us the color separation that we associate and find so beautiful with this thing that we call the rainbow. And so a really interesting and fun way to think about raindrops is little spherical prisms where we get these instances of reflection and refraction, and these just happen again and again and again until the light gradually fades out to black. And if we happen to be along the path where we can see one of these exiting refracted rays, we get to see the rainbow. It seems like with every refraction phenomena, there's some associated myth. Well, the rainbow's no different in that we've probably all heard of the idea of the pot of gold at the end of the rainbow. So is there any truth or is there any validity to that claim? Well, unfortunately for us, the answer is no. This thing that we call the rainbow is really based upon our perspective. If you remember from the primary bow, okay, the primary bow exists between 40 and 42 degrees. Well, what does between 40 and 42 degrees really mean? If I'm interested in the horizon, if I look straight up from the horizon, okay, think of this as 40 degrees above the horizon, and this is 42, okay, but what if instead of going up, I go to the left? This is 40 degrees left of straight ahead, and this is 42 degrees left of straight ahead. Or what if I went up and to the left? This is 40 degrees up and to the left from straight ahead. This is 42 degrees up and to the left from straight ahead. And so what the rainbow really is it's this band of color that always exists between these angles as measured relative to straight ahead. On the one hand, that's a little disappointing because, well, if you move, the rainbow you see moves with you. So that's a little bit disappointing in that we can never really get to the end of the rainbow because it shifts along with us. Okay, but it also means that anytime you see a rainbow, that rainbow is unique to you and your perspective. If you're standing next to a friend and say, hey, look at that rainbow, your friend can look out to the horizon and also see a rainbow, but the rainbow they see is based upon their perspective. Everybody sees their own rainbow. And this idea leads to another common misconception with rainbows. Some people have been fortunate enough to see this arch here and would claim that they would see a full rainbow. Well, in truth, this is actually only half a rainbow. A rainbow is this refraction and internal reflection phenomena that occurs along a band between 40 and 42 degrees for the primary bow, 52 and 54 and a half for the secondary bow, and so forth. But those angle measurements are really just degrees relative to looking off into the distance. And so what I'm getting at here is that the full rainbow actually isn't just that half of a circle, but it's actually a full continuous circle. These are far more rare to see because, well, normally the ground is in the way, blocking our view of the lower end of the rainbow. And so if we want to see the full rainbow, we need to find a location where we have 40 to 42 degrees of viewing angle that's below us. And that's what we have in this picture here. Here we can see the full rainbow. And if you look at the detail of the picture, okay, you can get a sense of where this picture was taken and why it makes the full rainbow visible. All right, we see a shadow here. All right, and this shadow is caused by the fact that there's a mountain. The person taking this picture is on a mountain, and specifically, they're up on top of a TV tower that overlooks a city on top of a mountain. Here you can see bright sunlight coming in from behind us, and off in the distance you can see thunderclouds. So what we have here is rain providing that mist that we need for that refraction and reflection to occur, and then we've got the sun behind us providing the light that will then be dispersed into the colors of the visible spectrum. Here's another example of almost a full rainbow. This was taken at Niagara Falls, okay, and you can see that we've got a wider field of view here, not quite the full 42 degrees below to give us the full 360, but pretty darn close. There's a couple other kind of light phenomena that resemble rainbows, all right, but that are a little bit different. Okay, this picture here, although we've got the full bow, is not a rainbow because it's not created by rain. This phenomena is called a halo, and what causes this is as you move up in the atmosphere, the temperature gets colder and colder, and eventually liquid water turns to ice. And that ice can be small enough to where it still stays suspended in the air, just like droplets in a cloud, all right? But since it's a solid, those ice crystals act like tiny little prisms to separate out the light into its colors. So think of this halo, okay, as a collection of tiny little ice crystals up in the air, and those colors are being separated out by this process of dispersion, which results from which results from refraction of white light into the colors of the visible spectrum. Now, if you're lucky enough to see one of these, okay, you want to avoid direct sunlight damaging your eyes. So what you want to do is hold your hand up and block the sun, and then that will also make the colors more vivid and protect your eyes from damage. We can have rainbows and halos formed by sunlight, but we can also get these things from moonlight. Now, moon halos and moonbows are less common than rainbows simply because, well, the moon reflects a lot of light, but it's still not going to be as bright as the sun is, all right? But if you're lucky enough to see the moon peering through the clouds, okay, you might just catch a moon halo. And the reason that this occurs is, well, clouds are just moisture. All right, and so those clouds are acting just like they would with sunlight, except they're separating light out into the colors of the visible spectrum by taking light that's been reflected off the surface of the moon. And finally, we can also have double moon halos, just like we can have double rainbows. And so what does it mean? To me, it means that refraction truly is phenomenal. This is Mr. Zarzak saying, thanks for watching the Glenbard West Physics Rainbow Screencast.